Deep neural networks, DNNs, have been a cornerstone in machine learning for their ability to learn complex features from data. However, the underlying mechanisms of this process are not yet fully understood. This research aims to shed light on how DNNs learn features, particularly through the lens of feature learning theories. A proposed macroscopic mechanical theory of feature learning accurately replicates a noise-non-linearity phase diagram, providing insight into why some DNNs are lazy, while others are active. This theory also explains how the distribution of feature learning across layers correlates with test accuracy. The authors introduce a spring block theory, where spring elongations represent data separation, and asymmetric friction models the propagation of signal and noise in both forward and backward passes. This approach offers a new perspective on how DNNs learn features, emphasizing the importance of noise and nonlinearity in the learning process. In essence, this research contributes to our understanding of DNNs' feature learning capabilities by highlighting the interplay between noise, nonlinearity, and the distribution of feature learning over layers. This knowledge can potentially guide the development of more efficient and effective DNN architectures in the future. The authors investigate the phenomenon of feature learning across layers in deep neural networks, DNNs. They define a load curve, DL, which measures the separation of data at each layer L, and demonstrate that modern overparameterized DNNs can exhibit different load curves depending on hyperparameter choices. The load curve is a discrete curve that represents the contribution of each layer to data separation. The authors show that nonlinearity and stochasticity in DNNs can significantly impact the load curve. They introduce a phase diagram that illustrates the relationship between nonlinearity and noise in DNNs. The diagram reveals that increasing nonlinearity results in concave load curves, where deeper layers learn better features, while adding noise to the dynamics rebalances the load across layers. Increasing noise leads to convex load curves, where shallower layers learn better features. The authors also examine the role of data separation in DNNs, defining it as the ratio of variance within and across classes. They demonstrate that data separation is a key factor in determining the load curve and that it can be affected by various factors, including nonlinearity, stochasticity, and hyperparameters. The results are visualized in Figure 1, which shows the phase diagrams of DNN load curves under different conditions, including varying levels of data noise, learning rate, dropout, and batch size. The background shading in the figure encodes test accuracy, and the results are averaged over 10 independent runs on the MNIST dataset. The authors' findings suggest that a stability argument can be used to link generalization and layer-wise data separation, and they show that this relationship holds true in real DNNs. They also discuss the implications of their results, including the importance of balancing nonlinearity and stochasticity in DNNs to achieve optimal performance. The analogy between a spring block chain and a deep neural network is striking, particularly in how increasing noise yields a linear and then a convex load curve, mirroring the effects of varying learning rate, dropout, and batch size on network dynamics. The concept of lazy training and the importance of nonlinearity and low noise in achieving concave load curves are crucial aspects. The spring block dynamics model is introduced, where each block's position represents data separation afforded by each layer. The equation of motion, including the effects of friction and noise, is explained. The phase diagram of the spring block system shows a striking similarity with the phase diagrams of real neural networks, highlighting the model's ability to explain concave load curves and lazy training. The concept of unbalanced equilibrium in a spring block system is analogous to lazy training in deep neural networks, DNNs, where the deepest layer learns most of the separation. However, with the introduction of noise, the load curve can become convex, indicating that shallow layers learn better than deep ones. The effective friction, which depends on the noise level, is defined and shown to be approximately independent of the initial position. This leads to a phase diagram for DNNs, where the condition micro greater than 0 corresponds to the transition from lazy to active training. The paper relates this condition to DNN phenomenology, highlighting how noise in the training process affects the learning dynamics. The spring block model, inspired by seismology and neuroscience, provides a novel phenomenological approach to understanding the dynamics of deep neural networks, DNNs. This simple model consists of a chain of blocks connected by springs, with friction at the interface between each block and the underlying surface. In the context of DNNs, the blocks represent the layers, while the springs and friction represent the interactions between these layers, and the external driving force corresponds to the input data. The model's behavior is determined by the interplay between the friction, the strength of the springs, and the external driving force, revealing that DNNs can exhibit different behaviors depending on the balance between nonlinearity and noise. A concave load curve characterized by the model's equilibrium state indicates overfitting when nonlinearity dominates, while a convex load curve suggests underfitting when noise dominates. A balanced combination of nonlinearity and noise results in a linear load curve, corresponding to optimal generalization performance. Equiseparation, a state where all blocks are evenly spaced, minimizes elastic potential energy and improves generalization. An experiment involving a convolutional neural network, CNN, on the fashion-MNIST dataset illustrates this concept. Initially, the CNN is trained using ADAM at a learning rate of 10 to the power of 4, resulting in a concave load curve and suboptimal test accuracy. By introducing a 5% dropout, the load curve becomes linear, and the test accuracy improves. However, increasing the dropout to 30% leads to a convex load curve and decreased generalization. This study demonstrates the value of both bottom-up and top-down, phenomenological approaches in deep learning theories. While traditional bottom-up analyses focus on the collective behavior of artificial neurons, top-down models like the Springblock model offer valuable insights into the complex interactions within DNNs, providing a new perspective on understanding feature learning, generalization, and conjectures worth pursuing rigorously. The authors present a comprehensive survey of state-of-the-art methods for tackling the complex problem of anomaly detection in high-dimensional data. This is a critical task, as anomalies can significantly impact the performance and reliability of machine learning models and data-driven systems. The authors categorize existing approaches into three main categories: supervised, semi-supervised, and unsupervised methods. Supervised methods rely on labeled data to train models that can identify anomalies, while semi-supervised methods leverage a combination of labeled and unlabeled data. Unsupervised methods, on the other hand, operate solely on unlabeled data, making them more versatile but also more challenging to implement. The authors also delve into various anomaly detection algorithms, including one-class SVM, local outlier factor, LOF, and isolation forest. These algorithms are compared and contrasted in terms of their strengths, weaknesses, and applicability to different types of data. Furthermore, the authors discuss the importance of evaluating anomaly detection methods using relevant metrics, such as precision, recall, and F1 score. They highlight the need for a comprehensive evaluation framework that takes into account the nuances of high-dimensional data. The survey also touches upon the challenges and limitations of existing methods, including the curse of dimensionality, class imbalance, and the lack of interpretability. The authors conclude by emphasizing the need for further research into anomaly detection methods that can effectively tackle these challenges and provide reliable results in real-world applications. Overall, this survey provides a thorough and systematic review of the current state of anomaly detection in high-dimensional data, highlighting the strengths and weaknesses of existing methods and identifying avenues for future research. Deep neural networks exhibit complex geometry, optimization, and generalization properties. Insights into their landscape can be gained through random matrix theory, which has been applied to study the geometry of neural network loss surfaces. 37. Shallow neural networks can be viewed as Wasserstein-type gradient flows. 38. While stochastic gradient descent introduces an effective landscape-dependent regularization, favoring flat solutions. 39. 40. Understanding generalization in deep learning models is crucial, and revisiting old ideas from statistical mechanics provides valuable insights. 51. Temperature balancing, layer-wise weight analysis, and neural network training are essential aspects of this understanding. 52. Lazy training in differentiable programming. 53, and micro-atomic scale vibration-induced superlubricity. 54, are also explored. In terms of optimization techniques, ADAM, a method for stochastic optimization, is mentioned. 55, as well as least angle regression. 58. Parallels are drawn between neural networks and seismicity models, emphasizing the importance of understanding neurons, dynamics, and computation. 56, 57. The universality laws for high-dimensional learning with random features are discussed. 48. Highlighting the significance of these laws in deep neural networks. For further details, the reader is referred to the supplemental material. 47. The experiment involving a folding ruler serves as an analog to the training dynamics of deep neural networks, DNNs, illustrating how noise can redistribute load imbalance caused by friction. This concept, known as lazy training, is characterized by the outer layers taking the largest proportion of the load. By shaking the ruler while pulling, it activates the inner layers, resulting in a more uniformly distributed extension of each layer. This mirrors the ability of DNNs to be trained for a more even distribution of the learning load. Numerical experiments and reproducibility are also discussed, including various settings for training DNNs and CNNs. These settings significantly affect the training dynamics, demonstrating the importance of understanding their impact on neural network performance. The experiment's findings underscore the importance of noise in optimizing neural network training, providing insights into the complex interplay between different layers and their role in achieving efficient learning. The paper discusses the concept of load curves in deep neural networks, which can be either convex or concave depending on the training regime. For regression tasks, the load curve is defined as the mean squared error, MSE, of an optimal linear regressor from the features of the LTH layer. The load curve for a 7 hidden layer ReLU network on the diabetes dataset shows that noisier training results in a convex load curve, while lazy training results in a concave curve. In the context of the second-order spring block system, the friction term is introduced to describe the dynamics of the blocks. This system exhibits two stages: an initial stage where the elastic force dominates, and a second stage where the spring force is balanced with friction, resulting in slow block motion towards the equilibrium point. The equilibrium point depends on the friction and spring constant, but not on the noise level. However, this stable point is reached only after an exponentially long time, making it undesirable for analysis. To avoid this issue, the paper suggests assuming bounded noise increments, applying noise decay, or introducing a stopping criterion such as a relative change threshold. These approaches are rooted in deep neural network practice, where common noise sources are bounded and relative change thresholds are often used. The phase diagram of the second-order spring block system is also presented, showing the relationship between friction and noise level. The diagram illustrates how different regions correspond to different types of load curves, providing insight into the interplay between these factors and their impact on the system's behavior. The authors present an alternative formulation of the Langevin dynamics, which involves adding noise to the velocity independently of the friction, resulting in a second-order Langevin equation. The position of the LTH block, XL, is governed by the equation of motion dx equals v dt, where the velocity VL is updated according to dVL equals k, Lx, Lf, VL, gamma VL, dt plus epsilon, t, dWL, t. The sliding friction F, V, is defined as a piecewise function, resisting movement with coefficients micro and micro for positive and negative velocities, respectively. The Wiener process WL, T, represents the noise, with epsilon controlling the noise level, which is decayed over time as epsilon T equals epsilon 0 e caret tau T, to ensure convergence. The friction at zero speed, F0, is defined similarly to the static friction FL in equation 9, but without considering noise. This dynamics can be solved using standard stochastic differential equation, SDE, integration methods. The authors present the resulting phase diagram in figure S4, which shows the behavior of the spring block system under this Langevin equation formulation.